This video will explain the coefficient of restitution. In our group, we have Everbrook Zoe, Gabby Nathanson as both testers, Daniel Lopez Villa as the calculator, and Justin Holmer as the driver. This test was performed on Friday, May 17, 2019. So first, what is the coefficient of restitution? It is a measure of energy loss between collisions of two objects along the line of impact, which is perpendicular to the plane of collision. This is the equation, and Daniel should explain it.
When a body collides with a material, the initial velocity should equal the final velocity. However, experimentally this is not the case. Experimentally, the final velocity is less than the initial velocity, and this ratio of velocities is known as the coefficient of restitution. In a two-body system, this can be thought of as the final relative velocity over the initial relative velocity of the system. Because energy is always lost during collision, the system can never be perfectly elastic, and therefore E can never equal 1. So E will always be greater than 0 and less than 1. So E can be thought of as the ratio of velocities and also as the ratio of energy. And the coefficient of restitution is useful for predicting the behavior of certain systems, such as in billiards, and also maximizing behavior, such as in golf, where the driver is engineered in such a way that the coefficient is as high as possible to give the furthest distance.
Our goal through this experiment is to understand how the coefficient of restitution varies with differing combinations of materials and to show that each collision between same materials should provide the same coefficient of restitution. We know it takes two objects for a collision, and thus the coefficient of restitution depends on the material for both objects. So for the first object, we chose the ball, and we had 5 materials to choose from: steel, nylon, Delrin, neoprene, and wood. And the other material was the base, acrylic or aluminum. Now we need to find a way to easily observe energy loss due to collisions along the line of impact. We will do this using freefall collision. Freefall utilizes relationship between gravitational potential energy and kinetic energy to record energy loss. At a certain height, there is potential energy which is converted to kinetic upon impact. That energy is then converted to potential after the impact. Thus, we can easily measure the change between the initial potential energy to final potential energy. Furthermore, the ball travels along the line of impact for the good majority of the run, so it is a good measurement. Here's Gabby performing one of the test runs.
The combinations we expected to bounce the worst and had the minimum values of E were the stainless steel and wood balls on either the acrylic or aluminum plates, and the expected value for the maximum E was the nylon on the acrylic and the Delrin on the aluminum plates. Each ball was dropped at an initial height of 39.5 inches above either plate, but we did not use this height as the H sub 1. Instead, we used the first bounce as H sub 1 and further on. The Delrin ball in the aluminum plate, E average came out as 0.886. The wood ball on aluminum plate was 0.651. The nylon ball on the acrylic plate was 0.817, and the neoprene ball on the aluminum plate was 0.544. The only coefficient of restitution value I found online was for the nylon ball on the acrylic plate, and that was 0.65, which is 20% less than the average that we found.
Sources of error. First, there's the camera error, where the nature of the lens sees the height of the ball differently than the actual height. This could be avoided by scaling the measurements to some degree, which we did. There could also be human error in releasing the ball in the initial height. However, we counteracted this by not counting the first height. Also, the plate cannot be perfectly perpendicular to the line of impact. We tried to put it on the ground to make it a little easier. Finally, there's air resistance, which we could do in a vacuum. Some discrepancies. Every collision between two materials should have the same coefficient of restitution in theory. However, our experimental data show that there was a 0.06 variation between collisions of the same material, as you can see from our experimental values. Furthermore, in theory, the ball should bounce forever, no matter how infinitesimal of a height. In experiment, height eventually reaches 0, meaning at some point coefficient of restitution equals 0. That contradicts theory. Also, collisions have 2 or 3 degree of motion and thus should have only translating motion in theory, but we observe slight rotation of the ball indicating energy is transferred into rotational momentum. Finally, in theory, the ball should bounce in the same spot for each collision, however we notice horizontal displacement in our testing. To wrap it up, we would like to thank Envision Studios and class MAE 130B for this experiment.